Hi, good evening. Am I audible clearly?
Yes, ma'am, you are audible.
Okay. So today we are going to discuss problems based on BJTs and MOSFETs. So before starting BJT and MOSFET based circuits, let's discuss the basics on BJT and MOSFET. So let's start with the differences between BJT and MOSFET. What all you recall about BJT and MOS? Okay, so what are the differences that you can recall?
Ma'am, BJT is a current controlled current source, and MOSFET is a voltage controlled current source.
Okay, so BJT is a current controlled current source. It can also be a voltage controlled current source depending on whether you are inserting base current or applying a base voltage, right? But rightly said, MOSFET is a voltage controlled current source, as here we cannot inject any current into the gate, right? What about number of terminals in these two
Ma'am, a
devices?
BJT has three terminals. MOSFET may have three or four terminals.
Yeah, BJT has three terminals, whereas MOSFET has ideally four terminals. But there is another body terminal which we short it to the source ideally, or we use it when we require. So it is used to change the threshold voltage and things like that. Okay, what else is different in these two? What about the polarity of the device?
Ma'am, BJT has more noise. MOSFET has less noise.
Okay, okay, you can say noise. What about the charge carriers that flow through in these two types of devices?
Ma'am, in BJT only both minority and majority carriers are there,
Yes,
while in MOSFET only majority carriers are there.
yes, both type of carriers are present in BJT, whereas only majority carriers. Or we can write it as bipolar, unipolar. What else? What about input impedances?
The MOSFET is going to have zero or actually very large input resistance, so current is zero in case of MOSFET input current,
Hmm.
and in case of BJT, there is finite resistance, and hence some current does flow inside the BJT input side.
So right, high input impedance and low input impedance. Okay, what else? Anything else that comes to your mind?
Ma'am, MOSFETs are small in size, while BJTs are bigger in size.
Can say, yeah, scaling, more scaling, comparatively less scaling.
Yes, ma'am, from coming from this, we can deduct that MOSFET can be mostly used in digital circuits, and BJT is mostly till now used in analog circuits.
But MOSFET can also be used in analog circuits.
Correct, but according to the current industrial requirements like that.
Yeah, yeah. So we can write it as digital and analog because we cannot ignore the analog counterpart, right?
Correct.
So here it's for, oh, sorry, it's only for analog. What else? Mm. What more can you think of?
Ma'am, in BGT there is thermal runaway, while in MOSFET there is no such phenomenon like that.
But there are also effects like punch through and all in MOSFETs also. So we cannot say it like that. So let's leave it. What else? What else can you think of? Okay, so let's talk about the region of operation, right? So for analog application, that is amplifiers and all, what is the region of operation?
Triode region.
Triode region.
Triode region.
Yeah.
Yeah.
Analog purposes we use
For
only
BJT, you are saying.
triode. Come again?
For BJT, you are saying that.
Yes, yes. Ma'am, it comes from the fact that we are going to
We
use
are
it
going to use it
in analog side,
in analog.
Ah,
analog devices,
okay.
and digital side we use
We use
MOSFETs. We
So,
are going to use switch side.
okay.
I mean
So for
on.
BJT, when we are going to use it as an amplifier,
Yeah,
it's
correct.
actually biased and forward active. Okay.
Yeah, correct.
It's not triode. Triode is used for MOSFETs. Okay. So
Okay, with terminology,
for
yeah.
BJT, yeah, we call it forward active. Okay. Whereas in MOSFET, region for amplifiers, let's say for amplifiers, what is the region of operation in case of MOSFETs?
Amplifier, ma'am. Actually, digital side we use it just
Use it
for
just for
switching on and off.
on and off.
So we are going to
So we
use
are going to use
saturation regions for that.
Okay, so for amplifier also you use it in saturation region, and in this course we'll explore MOSFET based amplifiers, so it will be even more clear. And when we talk about switch, so yeah, it's saturation and cutoff, right? Okay, what else is there? And if we talk about different regions in general in BJT, so in BJT we have forward active, saturation,
Reverse active and cutoff.
reverse active, and cutoff. What about in MOSFET?
Cutoff, triode, and
Yes, it's cutoff, triode, and saturation. Okay,
so
what
ma'am,
else? Yeah.
from all of this, we can almost find out that BJT is on a decline because most of the circuits nowadays are digital. MOS is
Actually, I.
industrially more used.
Wait. There is something wrong. Actually, I can hear your voice like twice. I don't know why.
Ma'am, two voices are coming, I think.
Yes.
I don't know how is that happening.
Okay. Yeah, come again. What was the question? Anyways.
I was saying that BJT is almost on decline and MOS is on a rise because most of the circuits nowadays,
Hmm.
85 percentage of the things are on digital and 15% or 10% on analog.
Yeah, but we cannot neglect the analog
No,
requirements,
ma'am,
right?
not neglect. I'm
Yeah.
saying it is on decline.
So that's why we also need to study BGT as well, because there are
Yeah,
certain uses where MOS cannot help. So that's where
correct.
we need to go for BGT. Okay, so since we have explored, something else that comes to your mind in terms of differences for these two devices?
Ma'am, come again.
Any other differences that you can think of?
Ma'am, MOS can be said more stable as compared to BJT. It
Sorry?
is more stable as in it can be easily controlled for a design as compared to analog.
MOS
Ma'am,
can
it's
be?
very delicate. Yeah.
No, I could not get you. Can you come again? What is it?
MOS is more controllable. मतलब, it's very sturdy, noise proof compared to
Okay.
analog.
Yeah. So that we have already mentioned.
Okay.
And yeah, so circuit symbols are also different. So this is how we represent a BJT, right? And when we talk about MOS, Okay. So these are the circuit symbols, right? So what about this first one? Okay, first of all, what is this arrow showing? What is the meaning of behind this arrow? What is
Sorry,
this?
ma'am.
What does this arrow signify in the circuit symbols
And
that we have?
direction of current.
Yes, it is the direction of current. So what type of BJT is this? First one.
NPN.
Yes, it is NPN, where this terminal is collective, base, and emitter, right? So since it is NPN, so this will be PNP with emitter, base, and collector, right?
Yes, ma'am.
So one thing that we need to keep in mind is always the current direction is given at the emitter terminal for BJTs. Okay,
Yes, ma'am.
always current direction is given to BJT's emitter terminal. Now talking about MOS symbols, so we have two sets of MOS symbols, right, which are most commonly used. So yeah, talking about this first set. So what is this MOS? What is the first one shown? So this is the current direction, right? So this is drain, gate, and source terminal, which makes it an NMOS. Okay. Now here again this is source terminal, because when we talk about MOS, the current direction is given to its source terminal. So this is source, this is drain, and this is gate. So which makes the second device symbol as a PMOS device. Okay. For simplicity, we also use this bubbled representation for PMOS and normal representation for NMOS. Was this clear?
Yes, ma'am.
Okay. And now coming to what about the current behaviors? How is the current, uh, like current and voltage relation in BJT and current and voltage relation in MOSFET? Do you have any idea regarding that? How is the current trend? So let's say input voltage versus output current if we are plotting. So how that curve will look like for the case of a BJT?
Exponential curve.
Yes,
Exponential
exponential.
for
Yes,
what?
ma'am.
It's dependent exponentially on VBE, मतलब input
So
voltage. VBE.
exponentially for BJT. Exponential for BJT, right? Exponential IV. What about for MOS? What is the trend?
The square of VGS
Yes.
minus VTH, and its saturation region square and
Yeah. And considering since VT is a constant, so it's actually quadratic relation, right? So quadratic IV. Okay. So these are the basic differences that we can think of in terms of BJT and MOSFET. So with these differences, let's move on to our problems. So the first problem is, see, for the circuit shown in this figure, identify the correct IV characteristics. So basically I have removed the options, so we have to draw it. Okay, so we need to draw the IV characteristics from which you can calculate small signal transconductance. Okay, so what is the curve it is basically talking about? From which curve will you get the transconductance?
current and output voltage.
Input current and output voltage.
Transconductance, no?
Transconductance. What is transconductance, first of all?
Ratio of current to voltage.
Yeah, so transconductance we denote it by G. It's the ratio of change in current versus change in voltage, right? So we want to find transconductance and denote it by Gm. So what what are the parameters? See here, if we see in this image, we have currents as IB, IC and IE, right? And when we talk about the voltages, we have VBE and VC. Now when you want to find transconductance from a characteristics, what is the combination that you will use, which current and which voltage to draw your IV?
IC and VBE.
So where will IC come and where will VB come?
On y-axis IC and
Okay.
in x-axis VBE.
Yeah, why we went for this combination? Like, what is the reason for selecting this combination?
Ma'am, so that we can keep VBE constant and check the change in IC.
No, no. So see, when we want to find transconductance, that is the transfer conductance, right? So it is a conductance between input and output pole, right? So where will you find this? So we need to have a graph which specifies the relation between input and output parameter, right? So when we say we'll find it using IC and VBA, that means what type of characteristics is this? This is a transfer characteristics, right?
Ma'am,
Because yeah,
there is some noise coming. I think someone's microphone is on.
uh, can everyone please check the microphones?
Ma'am, someone named NS is has disturbance in his mic.
Yeah, N NS. Uh,
Yes, ma'am.
can I request NS to please mute? Okay. Now, can you people? Acha, okay. So there was some noise issue. Now, can you people unmute? Like Arjun, you were talking, right? Can you unmute yourself?
Yes, ma'am.
Yeah, yeah. Okay. Now it is clear, right?
Yes, ma'am.
Okay, okay. Yeah. So what we were discussing? Yes. So we want transconductance. Okay. So for transconductance, you need to have a transfer characteristics. So it is a characteristics which will basically show the like the change in output parameter in terms of input parameter. And since we are going for conductance, we want to see the change in output current with respect to input voltage. Is this clear?
Yes, ma'am.
Okay, so that's why we are going for IC versus VBB. Now the next thing is, how will this characteristic look like? What will be the behavior of this characteristic? IC versus VBB.
Ma'am, exponential only.
Yes, it is exponential. So the behavior will be exponential. Okay, so what about IB versus VB? How is the behavior?
It's exponential as well.
Yes, it is also exponential, right? So this is what it was asked. Like, what is the behavior of IC as a function of VB? So this is known as transfer characteristics. So if this characteristics is known as transfer characteristics, what will this characteristics will be called? Like IB versus VB, what will we call this characteristics as?
Input IV characteristics.
Yes, it is input characteristics. And what about the characteristics between IC and VC will be called?
output IV characters.
Yes, output characteristics. And how does this look like?
So, ma'am, it's almost independent of VCE. Almost.
Yes, almost independent of VCE.
On a
Why?
slight curve, a
So,
slight
no, no.
slope.
Yeah. So what happens is it becomes almost independent of VCE in forward active mode. Okay. But what about in saturation region? It actually falls down. So this is the curve for saturation. Clear? So this is how your IC versus VCE looks like. And from looking at these curves, can you tell me what is the configuration of the device? So configuration, by configuration I mean whether it is common source, here it's like common emitter, common base, common collector. These are the three configurations we have, right, in terms of a BJT.
Common emitter.
Yes, how can you figure out that it is a common emitter configuration?
No, emitter is there for input side VPE and output side as well.
Yes, because here we can see that it is VBE as well as VCE. So E is common. That's why it is common emitter. Clear, right? All the characteristics, everything that we discussed till now, is this clear to everyone?
Yes, ma'am. Yes.
Okay, so let's move ahead. Now coming to the second question. Here, for the circuit shown, find the value of IB considering VBA as 0.6 volts, beta is 199. Okay, so what is this beta?
Gain.
Yes, what type of gain it is?
Current gain IC by IB.
Yes, current gain, it's IC by IB. So for this particular circuit, VBE is given. What do you mean by VBE? It's actually VB minus VE, right? So in the circuit, you know VBA and you know this beta, that is the ratio of IC and IB, and you have to find out IB. So how will we solve? Like, what is the first thought that you get when you look into this circuit? What is the thought that comes to your mind? So this is the current that we need to find out, right? So how will we solve it? So if this is IB, from here what is the current that is flowing? It's IC, and in this terminal it's IE. What is the relation between IC, IB and IE?
IE is equals to IC plus IB.
Yes, IC equal to IB plus IC. Now here you can see a potential and here there is a ground, right? So what we can do, we can simply apply a KVL in this loop. Can we do that? We can do this, right?
Yes,
So
ma'am.
if we write the KVL, how will it look like? It's like 12 volts is getting dropped across 470 kilo ohms into IB plus VBE plus 1 kilo ohm into IA. Correct? So here it will be 470 kilo ohms of IB plus VBE, which is 0.6, plus 1 kilo ohms into 200 of IB. Correct? So now here we only have a single variable. So from this equation we can simply get the IB. IB will be 670 milliamperes, right? So how much is this value? Can you calculate? What is the final answer? What is the final answer for IB?
0.017.
0.017.
17 microamps.
Yes. So this is in milliamperes. So IB will be 17 microamperes. Now moving on to next problem. So what it says, in the same circuit we have to find VE, that is voltage across the emitter. Now what is VE? How will we write VE in this circuit? In this particular circuit, how will we write VE?
IE into 1K. Can we write like that?
Yes. VE will be actually I into 1 kilo ohms. So what is the value of IE? It is 200 times of IB, right? We used this earlier also, into 1K. So that is 17 microamperes into 200 into 1K. So what is the value of V that you are getting? This will be 3.4 volts, right?
Yes, ma'am.
Yes. So these are the two linked questions. Now moving on to the next question. Okay. So in this problem, what it says is VI characteristics, like output characteristics, values have been given for different VC. What is the value of current IC? And IB has been given to be 20 microamperes. So we have to find out output conductance G0 at VC equal to 5 volts. So what is output conductance first of all? How will we write output conductance? Okay. Firstly, output conductance is the reciprocal of output resistance, right? How will we write output resistance?
Output voltage divided by output
Yes.
current.
So change in VC, because this is the output voltage, right? Versus change in current. So when we say G0, it will be simply DIC by DVC, right? So now we have to find G0 at 5 volts. So what are the values that we will select to find G0? See, we know that we need to see the differences in currents as well as voltages. So from these many values, what are the values that we'll pick to find the result? So since it is asked across 5 volts, so we'll look at one value this side, one value this side, closest of the two, right? And then we'll subtract it, and using the differences we'll divide those differences and find the value. So that means it will actually be 2.17 minus 2.11 by 0.6 minus 0.4, right? So this will be 0.06 by 0.2, and that is 0.6 by 2, which is 0.3. So G0 is 0.3. What will be the what will be the unit for this G0?
Siemens.
Is it Siemens? See, here this was in volts, right? Here it was in milliamperes. Okay, so here whatever we got is in millisiemens, it's not Siemens. These milli, micro, all these minute values have a huge importance. Okay, so you cannot miss, because it's order of 3 difference. Understand? So it's actually millisiemens, it's not Siemens. Clear?
Yes, ma'am.
Okay. So now, yeah, going ahead. Wait. Is this correct? We are doing right only, no?
Is 03, ma'am.
It's 03, right? Yeah, that's why. Yeah, so it's 03.03 millisiemens, or it is 30 microsiemens. Okay? Yeah. This is the final answer. So moving on to the next problem. So in this problem, now you have to find output resistance R0 looking into the collector terminal. So first of all, in this configuration, let's say A, B, C. What are the A, B, C terminals in terms of collector, emitter, gate, base? Which one is collector?
A is emitter, B
Yes.
is base,
So
and C
this
is
is
collector.
emitter, this is base, and this is collector. So what we have to find is R0 looking from here. So here VEB, why EB, why not BE? Because this is a PNP transistor, right? And here it is clearly evident that emitter is at higher potential than base. So that's why it is VEB. Clear? Beta is 180, VA is 72 volts. Okay. So we want to find R0. Okay. For R0, how we can write R0? We can write R0 as VA by IC. Okay. So for this, what first of all we need to find what is the IC, right? Once we find the IC, we can find like what is IC. Then we can simply find R0. So how the steps we will proceed for R0? We'll need IC. But can we find IC directly from this? Is there any way we can directly find IC from this particular circuit?
Yes, ma'am.
How?
No, ma'am, IS is not given.
Yes. So how we can find IC? Like what is the other method? What are the givens? By looking at given, can you think of something through which we can find IC? See, beta is given, right? So whenever beta is given, we know beta times IB will be IC. So if we can find IB, we can definitely find IC, right? Makes sense?
Yes, ma'am.
So let's first start by finding IB. So how will we write IB? IB will be the current coming from here. So let's say this is VB. So IB will be VB minus 5.4 by 500 kilo ohms. Correct? This is correct? I've simply applied the Ohm's law. है ना? Voltage by resistance is correct. Now VEB is known, which is actually VE minus VB. Here how much is VE? VE is 12 volts. So 0.6 equal to 12 minus VB. So how much is VB? It's actually 11.4 volts. Right? So we have got VB.
Yes, ma'am.
Now we can substitute it here. So IB will be 11.4 minus 5.4 by 500 kiloohms. So how much is the IB? How much is the IB that we are getting?
Twelve milliamperes.
Is it milli or micro?
Microamperes.
Yeah, 12 microamperes. See, it's very important. You cannot write milli as micro and micro as milli. It's thousand times difference, right? So now IB is found. So what will be IC? It's simply beta times IB. So how much it is? 180 into 12 microamperes. So how much is IC?
Two 2.16
2.16 watt.
milliamp.
Microamperes.
Is it milli or is it micro?
Milli, ma'am.
Milli, right? Because already we had 12 microamperes in which we are multiplying 180. So definitely it will change. It's like the unit will change, right? So it's
A micro.
2.1. Why micro? We are multiplying it with 180. So will it still be in micro?
It is 2160 microampere, which
Yes.
is 2.16 milliampere.
Is this clear? Arjun, I guess. Where is the confusion? Arjun, I guess it was you, right? Is it clear?
Yes, ma'am. It's clear.
It's clear, right? So it is milliamperes, right? Everyone is satisfied? Anyone has any confusions? No, right? So it is 2.116 milliamperes. So now we want to go for R0. R0 is simply VA, that is 72 volts by 2.16 milliamperes. So how much is R0? How much is the value of R0?
33.3.
Yes, 33.3 watt. See, you have to tell the units. You cannot write 33.3. It should be kilo, mega, milli, whatever it is. So what is the unit?
Milli, ma'am.
Kilo. Milli, yes, ma'am.
Milli?
Kilo ohm, sorry, nahin. Kilo ohms, yes, ma'am.
Kili के होगा.
It's 33.3 kilo ohm. मिली को जब रेसिप्रोकल करेंगे so it will be 10 to the power minus 3 goes up, right? So it will be 10 to the power plus 3 kilo ohms. So yeah,
Ma'am, what is R0? Can we read the question again?
yeah. So the question is, find the small signal output resistance R0 looking into collector terminal of the transistor.
Ma'am, since it is output resistance, so
Yes.
it should be output voltage divided by output current. So, ma'am, VA is
So
early
see,
voltage.
output sometimes, okay, logically it should be output voltage versus output current, okay? But actually whenever we talk about transconductance or resistance, it's actually change in voltages versus change in current, right? So if I say R0 is dV by di, okay? So what do you understand by early voltage? What is an early voltage?
Ma'am, we extend the curve to the back side
Yes.
to x-axis.
So what happens at early voltage? What happens?
Ma'am, it maybe dries goes into pinch off. I
No.
don't. No, I really don't know the
Okay,
concept of.
yeah, yeah. So, see, this is IC, this is VC. This graph is clear? Can you see?
Yes, ma'am.
So,
Yes, ma'am.
how does this curve look like? This is how our output characteristics look like, right? So now what we do, we say we are simply extending our curve such that it is meeting a voltage, we call it as a early voltage, where our current becomes 0. Okay, so we are simply extending this curve such that it meets voltage excess at a point where the current is 0. Here at VA you can clearly observe, right, current has gone to 0. Is this clear?
Yes,
Yes,
yes.
ma'am.
Yes,
So
ma'am.
when you extend the curve and current goes to 0, that voltage we call it as an early voltage. Okay, so we know this line is a straight line, right? So let's take 2 points, like here, uh, just beside 0 there will be some IC and VC is almost tending to 0, right? And here we have VA as the voltage and I is actually 0, IC is 0. So R naught is dVc by DIC, right? So VA minus 0 divided by 0 minus IC, right? So we can simply write R naught as VA upon IC minus. But does negative resistance make any sense? No, right? Resistances are absolute
Ma'am, where
values.
did the zero come from?
So yeah, we are saying so VA pe we know the output current is 0, right? And I have considered a current where, like, for the voltage VCA tending to 0, like very close to 0. ठीक है, so उस point पे I have considered this point which is tends to 0, so we can write it close to 0, and whatever is the current over there IC, I have mentioned that. Is this clear?
But the current is not existent at that point. I'll
You
read
can,
about.
you cannot say that. See, is it not, there is no necessity that it actually goes to 0 at VC equal to 0. It might or might not be. This curve might be shifted back. So then your curve will start from here itself. So maybe I can change the color. So your curve might start from here and it saturates at this point. That is also possible. This type of curves are also available. But it depends what we are talking about. Okay? So that's why I was saying कि we are considering a small voltage where there is non-zero current, but the voltage tends to 0. Okay? So at that point we can simply write it as VA by IC, and if I take mod of R naught, then it will simply be VA by IC, right? So actually I wanted to show how we come to this conclusion, like how we can write R naught as VA by IC safely, because when we can have dVc by DIC, so earlier when we were finding this output conductance, right, in this problem, here we had the values of different VCs and different ICs. So for finding R naught, here I'll simply go for dVc by DIC, right? And here, since I have different values of VCA as well as IC, I can simply take the differences and divide them, right? But in this problem, can you find different values of VC? Can you do that?
Exactly. That is why we are considering that
Yes,
known points.
yes,
Right. I got it.
because VA is given. So we have to work on a problem depending on what are the given values, right? always we work on. That's why it's very necessary to jot down what are the givens, because always you proceed by solving a problem according to what are the values which are given. Now here, since VA was given, that's why we are going for this formula. But other than this, like in above question, if this type of chart would have been given, I would have gone for simply this difference method, right? Is this clear?
Ma'am,
Yes,
slight
ma'am.
मतलब, modification can we do, ma'am, since we now have IC?
Mm-hmm.
Can we take the VC at this point? मतलब, since we know the IC right now,
Okay.
one of the ICs we know,
Hmm.
that side we know at VA IC is 0, correct?
No.
But right now we have some IC. At this point, we can find out VCE and find the difference. It will give more accurate results.
Okay, yeah, I understand. So basically, you are saying like R naught, can we write it as VA minus VC by 0 minus IC?
Yeah, can
This
we
is
do
what
that?
you,
Yeah.
yeah, this is even accurate. I agree. This also you can do, but for this, you need to calculate VCE also. In this circuit, how will you calculate the VCE? It is very difficult, right, in this particular circuit, because there is no resistor in this loop. So we don't actually know, okay, what are the actual voltages of like VE and VC. So that's why we cannot find VC over here. So we are going for a simple
Yeah,
method.
VC will be directly
12
VC
volts.
minus VE, and
So
that will
you will
be
write
12
it as a
minus.
12 volt.
Sorry.
So you will write it as 12 volt. That's what you are saying.
Can't be right, and I'm just asking because VC minus VE, that means VC is 0 and
0 and VE is 12 volts. So
yeah.
can't we write VEC as 12 volts?
Uh,
Uh,
I'm just asking. I don't
no,
know.
no, you cannot write. And 12 volts is quite high also. So it
Okay,
will,
no problem.
the junction cannot handle, and we cannot write it like that also.
Okay.
Yeah. If here there were resistors, then we would have written like the drops across those resistors, and we would have found out, okay, what is the VC that we would have done. But yeah, here we cannot write it like that. And this is actually a like well established formula also for R note. We generally use it like VA upon IC. Even when we look into MOSFET, we have similar kind of formula there as well, considering the early voltage. Yeah.
Yeah, ma'am, got it.
You
Yeah,
got
thanks
it?
for. Yeah,
Okay.
ma'am.
Yeah. So it
Ma'am, thank
depends.
you so much for clarifying this much.
No,
I
no, it's okay.
lot.
But yeah, so basically, how you solve a problem depends on what are the given values to you. So if VA was not given, I would have never thought of this idea, right? Okay, we'll solve the output resistance using VA. So it comes out from what are the givens. So it generally gives you the direction how to solve a problem. That is the thing. Okay. So is this clear to everyone? Whatever we have done till now,
Yes, ma'am.
how we found out R naught? Yeah. So moving on to the
Yes.
next problem. So in this problem, we have to find the minimum base current required to drive the transistor into saturation region. And it's given that, okay, first let's write down the gains. It's given that VC sat is 0.3 volts. Again, this transistor is PNP. So this is emitter, base, collector. Beta is 130. Now we have to find the minimum IV such that this transistor is in saturation. What do we mean by saturation? Saturation region of operation in BJT. Yeah, what is the basic sense behind saturation region of operation in a BJT?
Where the current becomes constant at the output.
Mm, No, I'm talking about in voltage terms. What can we say in voltage terms? Or talking about the two junctions, how will the two junctions be? So we have two junctions, right? Base collector and base emitter. So how will these junctions will be? Whether they will be forward biased, reverse biased, no bias? What will be the situation?
Reverse, ma'am.
Reverse
One will
bias?
be in one will be in
We want our transistor to be in saturation region.
Collector base, emitter base will be forward bias and collector base will be reverse bias.
No. Okay. See.
Only condition left for saturation is if both are in forward bias.
Yes. So this is very important to know. See, here it was changed to saturation region. Till now what we were doing, we were considering forward active. So that's why it is very necessary to know, okay, what will be the condition. So when we talk about saturation region, both junctions will be forward biased. When we talk about forward active, emitter base junction forward biased, collector base junction reverse biased. When we talk about cutoff, emitter base junction is reverse bias, collector base is also reverse bias. And when it is reverse active, emitter base will be reverse bias and collector base will be forward bias. This is something we need to keep in mind, okay? So most of the time we work in forward active, but when it is particularly mentioned that it's in saturation, we need to know that what is the condition for saturation. Is this clear?
yes, ma'am.
Yeah. So in this structure we have to find the base current such that our this transistor is in saturation. Okay, so if we talk about VEC is given. VEC is given. That means V minus VC, right? So V we can simply write it as 12, and VC how we will write? We'll write VC as IC into 2 kilo ohms, right? This is how we'll write VC, and this VC sat is actually given 0.3 volts. So from here can we find IC? It's 12 minus 0.3 by 2 kilo ohms. How much is the IC that we are getting? How much is the IC that we are getting?
Five 5.85 milliampere.
5.85 milliamperes, right? So now we have found out IC. What else is given? Beta is given to us, and we need to find IB. We can simply find IB, right? IC by beta. So it is 5.85 by 130. How much is this? How much is the IB?
0.0545.
Yeah, 45 microamperes. Okay, this is clear?
Yes, ma'am.
This is clear, right? So moving on to the next problem. In this, here again writing down the given, alpha is given to be 0.995, VBE is given 0.6 volts, Find the value of collector current, that is IC. So what is alpha? Yes, what is alpha?
IC upon IE.
Yes, alpha is IC upon IE. If I want to write everything in terms of beta, I'll simply write as beta IB upon beta plus 1 IB, right? So if I want to calculate beta in terms of alpha, how much is the beta? Like, how will you write beta? So here it is, beta upon 1 plus beta is alpha. This is clear how we got this?
Yes, ma'am.
So now I want the value of beta in terms of alpha. Can you do that? We have to simply rearrange these two, and here I want the value of beta in terms of alpha.
In the place of beta, we are going to
Alpha
write
upon alpha
alpha as
minus
1.
1.
Yes, alpha upon, sorry, somebody was saying something.
Alpha minus 1.
Alpha upon alpha minus 1. Yes, it is alpha. Is it alpha minus 1 or 1 minus alpha?
Sorry, 1 minus alpha. Yes, ma'am.
Yes, it is 1 minus alpha. So this is the relation between alpha and beta. So what will be the value of beta? You'll simply substitute, right? So how much is beta that we are getting? It's 199. I've calculated it already. It's 199, right?
Yes, ma'am.
Okay. So we ultimately we have found out what is the value of beta. We know VBE. What we need to find is IC, right? So again we can apply a KVL like this, right? So one more question. Why am I going always for this KVL and not for this direct KVL? Why am I always going for this KVL? Can I go for this one? Like path 1 and path 2. What about path 2?
VC is not available.
Yes,
We know VB.
we cannot go for it because this voltage that is VC is unknown to us. Is this clear? That's why I am going for this path 1. Clear, right?
Yes, ma'am.
Okay.
Yes, ma'am.
So across, how will we write the KVL here? KVL for path 1, it is like 12 volts equal to, okay, what is the current across this 1 kilo?
IC.
IB plus IC.
Is it IC or is it IB plus IC?
Ma'am, there is a split at that point, so it is we are applying KCL.
Yes, actually में यहाँ पे you will have IB, right? So when you apply KCL at this point, you will actually find the current is IC plus IB. The split is very important, so you need to know where the split is coming. If for suppose if it was like this, ठीक है, rather than this split, if it was like this, then what will be the current? I'll maybe change the color. रुको. Then what is the current across 1 kilo ohms?
IC.
IC.
Yes. So here the current is IC because there is no splitting. So the current which is flowing through collector is same current that is flowing through 1 kilo ohm. This is clear to everyone?
Yes, ma'am.
Yes, so this is very important to understand where the current is splitting and what current we are going to use. So here actually it is IC plus IB. So we'll write it as 1 kilo ohm into IC plus IB plus 197K into IB plus VBE VEB. Yes, VBE VEB.
VBE.
VBE. Why? Because it is an NPN transistor. Clear enough? VBE or
Yes, ma'am.
VEB का concept. Okay. And then IE 1 kilo ohms into IE, or I can simply write it as IC plus IB, right? So here what was asked is collector current. So I'll convert this whole equation into collector's current. Okay? So I'll only have one variable. So it is IC 1 plus 1 upon 199 plus 197 into IC upon 199 VB plus 1 kilo ohm to 1 plus 1 by 199 into IC. So here we only have one variable, that is IC. So we need to solve this equation and find the value of IC. Can you quickly solve this equation? And let me know what is the value of IC. So here VB is 0.6. And replace it with 0.6. So yeah. Or if it looks very dangerous, what you can do, you can simplify it in forms of IB. That will make the equation look very decent and easy. So it will be simply 200 plus 197 into IB plus 0.6 into 1K.
5.66 milliamperes.
Okay, 5.66.
66.
Okay, let's wait for others. What about others? Into IB. So from here you will find IB, then simply multiply it with 199. You will get IC. That also you can do. Both ways we can work out. How much are you saying?
5.66 milliamperes.
Actually, I'm getting 3.8 milliamperes. Maybe can you recheck it once? Solve it using this IB formula.
Now it's almost around 3.794 IC.
3.794, right? So 3.8 milliamperes. Yeah. Maybe you can cross check it once. Actually, IC that I'm getting is 3.8 milliamperes.
Yes, ma'am. IB came around 19.07 microamperes. It came from 11.4 divided by 597.
Yeah,
So,
yeah. Others, can you please respond? If all of you have got the same answers, maybe we can move ahead. Or is there... This equation is clear, right? So there might be some calculation mistake.
Yes, ma'am.
Are you getting it? All of you?
Yes, ma'am.
Okay, so shall we move ahead?
Yes, ma'am.
Okay. So moving on to the next problem. So, okay, so what has changed here in this problem?
There is MOSFET.
Yes, earlier we had BJTs, now we are starting to solve MOSFET based questions. So first things first, we need to know what is the current equation for MOSFET. Yes. What is the current equation for the MOSFET? ID equal to any one current equation that you remember in any region. Let it be linear or triode, saturation, any one.
ma'am, it's mu n epsilon by T ox multiplied by W by twice L I VGS minus VTH the whole square in saturation.
Okay, this is in saturation. So anyone want to try for triode region? Like what is the current in triode region? This is for saturation. What about triode? Or we can simply write it as C ox also. Is triode region anyone? Do you know or not?
No, ma'am.
So you don't know? You only know saturation?
Ma'am, it's VGS minus VTH minus VDS by 2 multiplied by VDS and 2 factor is not there outside.
Yes, yes. So it's like mu and C ox. W by L. VGS minus VTH minus VDS by 2 into VDS. So this is for triode region. Or it's like universal equation, okay? So the basic, whenever you derive, you'll get this equation. And talking about linear, so what changes in linear? Like what is different when we say it is in linear, saturation or triode? What is it that is basically changing?
Can you repeat the question?
So when we talk about a MOSFET, we say the MOSFET is in saturation region, triode region, linear region, right? What is that condition that makes the transistor to be in saturation, triode or linear region? What is it?
Pinch off occurs when VDS becomes greater than VGS minus VTH.
So that is for saturation. So what is the factor that is basically defining the operation? It is this VDS, right? Is this clear what I am trying to say? Are you getting it? So basically, what is the condition for saturation? This is the easiest one. VGS should be greater than VTH. This is to turn on the transistor. This is clear, Anna? Now what is the actual condition for saturation? VGS minus VTH should be less than VDS, right? So here basically this VDS is the one that defines, okay, what is the region of transistor. Now if I say linear, that means here also VGS will be greater than VTH, but VDS will be much less than VGS minus VTH. Okay, so what happens now if I, let's say, expand this VGS minus VTH into VDS minus VDS square by 2. This is how it will look like, the universal equation. Now in linear region, what happens, your VDS is very small. So when it is very small, the square of a small term will even be very small. Okay, like 2 का square is 4, but what about 0.1 का square? What about 0.1 का square?
It's less than 0.1,
Yes,
0.01.
it's 0.01, right? So it's much less. So that is the idea that we use here. So we say since VDS is small, VDS square will be very small or tends to 0. So we simply ignore this, and in linear region we simply write our current equation as this. This is linear. Is this clear? Is this clear what I am talking about over here? Are the current equations clear?
Yes, ma'am.
And also the conditions are clear, like when we say the transistor is in saturation and when we say the transistor is in linear. Is this clear?
Yes, ma'am.
Okay. And when we put
Ma'am,
in,
ma'am, can you please explain what is triode region? I don't know.
okay, so triode region is basically, it's neither in the transistor is neither in saturation nor in linear. So if I make the output characteristics, this is how your output characteristics look like. So this is saturation region, okay, the flat region. This ramping region is actually a linear region, but here there is a curvature, you can see, right? It's neither flat nor ramping in this region, है ना? So this is where we call it as a triode region. Okay, so when VDS is very small, you can simply apply this equation of linear region, or otherwise if VDS is like almost comparable, then you can also apply this triode current equation. Clear?
Yes, ma'am.
It depends on what is the value of VDS. How small is your VDS, it will enable your linear equation. Or if the VDS is comparable to VGS minus VTH but it is less, then we'll go for triode equation. Is this clear? And saturation का तो condition है different है. So if whenever you see that the conditions are satisfied for saturation, you'll simply go for saturation. Fine?
Yes, ma'am.
So now coming back to the question. So what is given in this question? The values have been given. UNC XW by L is given. VTH is given. Lambda is 0. Lambda comes from channel length modulation. We'll discuss it in coming weeks. Okay, so here we don't have to, so we are considering the transistor to be ideal. It doesn't show any second order effects. Okay, that means this region in saturation is completely flat. That is the assumption that we are taking. That's why the lambda is 0. This shows lambda is 0. When this has a slight slope, let's say like this, here lambda is not equal to 0. Is this clear? So whenever lambda is 0, that means these conditions, these equations are valid. When lambda is not equal to 0, the equations will also change. Okay, are you getting it? Okay.
Yes, ma'am.
So now let's move on. So we have to solve like R1 is equal to R2. These two are equal. So what is the voltage at this point if these two are equal? What is the value that you'll get?
1 volt.
1 volt.
Yeah.
So here you have 1 volt. So okay, since I'll maybe solve it here. So how much will be the VGS minus VTH? How much is the VTH minus VTH? VGS minus VTH? 1 volt minus 0.5 volts, so it is 0.5 volts. So what we have to find is find the maximum value of resistance R. Okay, this R is unknown. Maybe I'll okay, so in this what we have to find is R. R is unknown. Okay, now we know VGS minus VTH is 1 volt. Okay, mu and C ox W by L is given to be how much? 1 milliampere per volt square. 1 milliampere per volt square. Okay, so, and it is known that transistor is in saturation. So ID will be, what is the formula that we'll use for ID? NC ox divided by 2L VGS minus VTH whole square, right? This is the formula that we'll apply. So when we are applying this formula, how much is the ID that we get? How much is the ID that we are getting? Yes, what is the ID that we are getting?
Is it 0.125 milliamps?
How much is it?
125.
0.125 milliamps.
Yeah.
Okay. So is everyone getting this value?
Yes, ma'am, same.
Same value? Okay. Now we need to find this resistor R, right? So let's apply KVL for this loop starting from 2 volts to ground. So 2 volts will look like, will drop across ID into R plus VDS, right? Now since the transistor should be in saturation, so what is the condition for saturation? VGS minus VTH should be less than or equal to VDS, right? So let's consider it to be equal to VDS. This is where the pinch off starts, or like the saturation starts. So considering this, our VDS is how much? 0.5 volts, right? VDS will be 0.5 volts. So how much will be the value of R? It will be 2 minus 0.5 by ID, right? So from here, how much is the value of R that you are getting? How much is the R that you are getting?
12 ohms, ma'am.
12 ohms.
Milliohms.
What is
Kilo ohms, ma'am.
milli ohms? कैसे होगा? ID is in milliamperes, so it will go above, right? So it will be kilo ohms, right?
Kilo ohms, ma'am.
Yeah. Now tell me, is this R max or R min? Is this value of 12 kilo ohm, is it R max or R min?
R max.
R max.
Yes, ma'am.
Is somebody who wants to say this is R min? Okay, so can you explain why it is R max, not R min?
Ma'am, it will be R max because if we increase the resistance even further, the drop will increase and hence the VDS will decrease.
Yes,
It will drive to the limit.
yes, so that's why it is R max. And in question also it was asked what is the R max, like maximum value of resistance. So that's why the moment we started with it, we could get the maximum resistance. So this R can be, for keeping this transistor in saturation, R should be less than equal to 12 kilo ohms. Is this clear to everyone?
Yes, ma'am.
Yes, okay. Now moving ahead. So in this problem, this is a very simple problem, okay? So you have to find the correct options for a PMOS transistor to operate in saturation region. What is the condition for PMOS transistor to operate in saturation region? Yes. Okay, don't look at the options. Let's just discuss. What are the conditions we'll need to check that the transistor is in saturation or not? Or especially the MOSFET is in saturation or not? What are the conditions?
VDS is more than VGS minus VTH.
VDS is more than VGS minus VTH. What else? More than equal to. Yeah. What else? See, this is the main condition, but you should never forget VGS should be greater than VTH. This is also a must. If this is satisfied but this is not, then your transistor isn't actually cut off. Okay, so always whenever it is asked, you need to check for both of this to find it in saturation. Or if you want to say a transistor is in saturation, it's definite to show both these conditions should come true, then only your transistor is actually in saturation. If this comes true but this comes false, that means your transistor is not even on. So how is it in saturation, right? This is the first condition that you should check, and this is the second. Is this clear to everyone?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So you should always check for these two. Now this is for what type of MOSFET? This is actually the
NMOS.
condition for NMOS. Now you have to write the conditions for PMOS. So how will you write? What are the things that will basically change for PMOS? What is it that will change when we change the transistor from an NMOS to PMOS?
Ma'am, polarities are reversed, so
Yes,
VSP should be.
source will become drain and drain will become source. So subscripts will flip. Okay. So if I write VSD should be greater than equal to VSG minus VTH. Is this correct for PMOS? And VSG greater than VTH. Is this correct for PMOS? What do you think? See, there are two
Can you
options.
explain it again, ma'am?
So for PMOS, as you people said, subscripts will interchange, right? So I have, for DS I have made it SD, for GS I have made it SG. So I come up with these equations, right? These two. Now what I am asking is, are these two equations correct for PMOS? Yes or no? There will be two options, and in this I want the response from each and every one of you. Is this correct or incorrect? Yes or no? If yes, why? If no, why not?
VTH minus VSG or VSG minus VTH, no?
Hmm, like VSG minus VTH. So whatever
Okay.
I have written here under these curly brackets, these two equations, is it correct or not?
it will come minus VTH, no?
Minus VTH. Okay, so you mean here I'll put another minus. That's what you mean?
Yes, ma'am.
So that will make here a plus. Minus minus plus. So if I put another minus over here, then it will be VSD should be greater than equal to VSG plus VTH. Is it correct?
Just a second, I'll check.
Ma'am, we need to use the mod.
Yes, this is not correct. This is completely wrong. So what we will do instead, we'll put mod. So that will make the VTH positive, because for PMOS the gate voltage is negative, right? So we should always use a mod. Is this clear to everyone? To check the
Yes, ma'am.
conditions. Now here when you see for a PMOS, this is how a PMOS is connected, okay? And most of this times it is VDD, and this is connected to, let's say, ground, and this is VG. So, and this is drain, this is source. So here source is at higher potential, drain is at lower potential. So VSD is positive. Similarly for VSG, this thing is also positive because source is at higher potential than gate. But when we talk about VTH, for PMOS, VTH is always a negative term. So we need to use a mod so that all the terms in our equation are positive. So the signs are balanced. Is this clear? Since this term is positive, this term is positive, this term should always also be positive, right? To balance the sign in this equation.
Yes, ma'am.
So that's why a mod is required. Is this clear to
Okay, ma'am.
everyone? So
Yes, ma'am.
yeah, so these are the equations for PMOS. So what are the options that we'll get from the 5 options? What are the correct options, correct answers?
A.
A? A for PMOS.
B,
B,
ma'am.
B1.
Yes, it is B. And what else?
C also, ma'am.
C also. So it's actually B and C. Clear?
Yes, ma'am.
So whatever we discussed here regarding mod and everything, is it clear to everyone?
Yes, ma'am.
Okay, so let's move ahead. Now coming to this question. So in this question, this is the circuit given. Here again your mu p. Acha, what type of transistor is this? What type of transistor is this?
NMOS.
NMOS? Is it an NMOS? How will you find out what type of MOS it is? Depending on the arrow, okay? If the arrow is going inward, then it means it's a PMOS. If the arrow was going outward, that means it's an NMOS. So in earlier question, last question, this was a NMOS, but here we have a PMOS, okay? Is this clear?
Yes, ma'am.
So here we have a PMOS. Now secondly, Rn is given 9 kilo ohms, Rd is given 18 kilo ohms, VTHP is given 0.5 minus 0.5 volts. Maybe CX by L is 0.5 milliampere per volt square. IST is given to be 90 microamps. So you have to find R2. Now for this amount of current, what will be the value of R2? Okay? So how will we find it? first of all, since current is given, so let's start with the current. Okay, now how will you know whether the transistor is in saturation or linear? Can you tell anything about this? So this is source, gate and drain terminal, right? So can you talk about the region of operation of this transistor, whether this transistor is in linear region or like or in saturation region? Can you say anything about that, or in triode region?
It is in linear, ma'am.
How do you know?
Because it is functioning.
Because it is. I could not get you. What do you mean by it is functioning? See, how do you find out whether a transistor is in saturation or is in linear region? For PMOS, you need to know VSG should be greater than or equal to VSG minus mod of VTH, right? For it to work as saturation. So this is the condition that you need to know. And since actually it is working and giving current, so that means VSG is greater than VTH. That is obvious. Because it is giving a current, that means this is obvious, right? So now this is the condition that we need to check. So can you check this condition and tell me whether the transistor is in saturation or not? Yes? Is it even possible to check this condition? Students, are you there with me?
Ma'am, we need to check whether the source is at higher potential as compared to gate and drain, which we can do by RD multiplied by ID is available. RD is also available.
Okay.
2 minus RD into ID will give some value which will be available at the source point. So we
Source
can,
point, though, you know it is 2 volts. Drain by you will get the voltage. I agree. What
yeah, yeah.
about gate? Do you know the potential over here?
No current will flow in.
But for finding VGS, when we write VGS or let's say VSG, what does it actually mean? It means Vs minus Vg, right? So we need to know this Vg, right? That is the potential at this point. So do you know the potential at this point?
No, right now we don't know.
No, right? So can we guess what is the operation of like region of operation for this transistor?
We'll assume something.
Actually no. Yeah, so we'll really assume it. So let's assume. What should we assume? Do you want to assume it saturation? Do you want to assume it to be in saturation? Chalo, let's assume it to be in saturation. So ID is mu1 COX W upon 12 VGS minus VTH mod VSG this will be also VP whole square. This is what the formula is, right? You know ID, you know this term, you know Vs, you don't know Vg, and VTH you know. So by solving this, you'll get the values for Vg, right? And since it is a square quadratic, while solving you'll get two values for Vg. So can you quickly solve the values and tell me? So ID is like 90 microamps is equal to 0.5 by 2 into Vs is 2 minus Vg minus 0.5 square. So you have to solve this equation and let me know the values of Vg, and you'll get two values. What are the two values for Vg? What is the value of Vg that you are getting? Are you there, student?
16.47, ma'am.
Vg you are getting 16.47 watt
Volts.
volts. Seriously, 16.47 volts you are getting. Okay, can Vg be more than 2 volts? Supply is 2 volts, right?
Millivolts, ma'am.
So you are getting 16.47 millivolts. What about the other
Yes,
answer?
ma'am.
What about the other answer?
Ma'am, is it 3.1 or minus 0.1?
Vg how much?
I'm not sure, maybe something is wrong, but around 3.1 and minus 0.1 like that.
So ultimately what you should get, Vg should come out to be 1.1. That means 2 minus Vg should be 1.1. मतलब Vg should be 0.9. ठीक है, ये आना चाहिए. Are you getting this? Is anyone getting Vg to be 0.9?
Yes, ma'am.
What are you getting?
0.9 volts
Are you getting
as
0.9?
Vg. 2 minus Vg is equals to 1.1. So if you substitute Vg as this one.
So what about others?
Yes, ma'am, we are getting
0.9 you people are getting?
Yeah.
So yeah. So once you got Vg to be 0.9 and Vsg to be 1.1 volts, right? Now we assumed our transistor to be in saturation. Okay. So let's check what about VSD. So how will you write VSD? It's 2 minus IDRD. VSD is 2 minus IDRD. Is this clear? So that is 2 minus 90 microamps into how much is RD? 18 kilo ohms. So how much is the VSD that you are getting? How much is the VSD?
Is it 0.38?
Yes, 0.38 volts. Okay, so what is the condition for saturation? VSD should be greater than equal to VSG minus mod of VTH, right? Now let's substitute. VSG minus VTH कितना आएगा? We'll have 1.1 minus how much is VTH? 0.5? 0.5. So how much is it? How much will we get? 0.6. This is VSG minus mod of VTH, right? And VSD is 0.38 volts. It is less than 0.6, right? Or if I write it in this way, so it is not equal to greater than equal to 0.6 volts. Clear? So this shows transistor is not in saturation. Is this clear?
Yes, ma'am.
We are basically cross-checking our assumption, if our assumption is correct or not. So it turns out that our assumption is wrong. Now again let's assume transistor. See, if transistor is not in saturation, definitely it's in linear or triode region. And when it is triode region, we can simply apply ID to be mu n C of W by L, VGS minus VTH. Let me write it for P. VSG minus mod VTH minus mod VSD by 2 into VSD. Okay, so we'll apply this formula. VSD we know, okay. ID we know, it is 90 microamps. This value is 0.5 into 2 minus VG minus 0.5 minus 0.38 by 2 into 0.38. So what is the value of VG that you are getting from here? What is the value of VG? See, here it is a linear equation, right? There is only single variable, no quadratic, no nothing. Okay, so you have to simply find this value. What is the value of VG that you are getting? What is the value that you are getting? It should actually be 0.836 volts. Are you getting this value? Anyone? students, are you there?
Yeah, ma'am, we are getting.
Are you getting 0.836?
Yeah, 0.837 almost.
You are getting 0.836, no? Now
Yeah.
see, what was there? There was R1, R2, and here there is Vg, right? And here you have 2 volts. You are given that R1 is 9 kilo ohms. You have to find R2. So, and you know this value. So how will you find R2? So 0.836 is actually R2 upon R1 plus R2 into 2, right? It's a simple voltage divider, right? Resistor divider circuit. From there we can say write this, है ना? Now here R2 is what we need to find out, and we already know R1.
Okay.
So we have to solve this equation to find the value of R2. So how much is the value of R2 that we are getting? The problems are easy. It's just that you need to do the calculations, and you need to be a little patient, because even a plus minus mistake will ruin the answer. So that's why take your time, it's okay.
Ma'am, is it 6.46
Yes, 6.46. What is the unit?
kilo ohms?
6.46 kilo ohms, or we can safely say R2 to be 6.5 kilo ohms. Right? Did everyone get this? Any doubts? See, we have solved 10 questions till now. Do you have any doubts in any question?
Actually, maybe I have to refer the videos of the sir. I have
Okay.
not referred the videos,
Okay.
so maybe I'm lagging there, ma'am.
In what sense, if I can help you, maybe?
No, I didn't have any time because I have joined as a lateral entry after diploma.
Okay.
So there are assignments and all. So I was
Yeah.
joining for just problems session.
Okay, so maybe you can uh, go through the lectures, and it's better if you go through the lectures beforehand, so that when you come here you are a little prepared and you can ask whatever questions you have, right?
Yes, ma'am.
Okay, so any further questions, or do you want me to go to the next question?
Yes, ma'am. Next question.
Okay, so in this question what we have to find is, find the value of current ISD flowing through 10 kilo ohms. Okay, what type of MOSFET is this?
NMOS.
Is it NMOS?
ഓ PMOS പിന്നെ.
Yeah, it's a PMOS. So this is source, drain, gate. So let me ask you, how about by looking at this configuration, what do you think? Is this transistor in saturation or not?
சீக்கிரமா
So
நடத்திட்டு போ.
what is the condition for transistor to be in saturation? VSD should be greater than or equal to VSG minus mod of VTH, right? Vs is common, so we can simply remove Vs. So here you can clearly see that Vd and Vg are shorted, right? So this configuration is always in saturation. Can you mute yourself? Somebody is unmute and noise is coming. Okay, so is this clear when I say that this configuration will always be in saturation? Why is it always in saturation? That is because the drain and gate are shorted. So when drain and gate are shorted, that means VSG greater than or equal to VSG minus VTH, and this is always true, right? Is this clear what I'm saying?
Yes, ma'am.
So simply we are now we are confirmed that this is in saturation, so we'll simply write the formula for ID, that is NCoxW by 2L VGS minus VTH of whole square. So here VTH is given to be 0.5. You need to find ID. Mu and Cox is given to be 1 by 2 milliamps per whole square. VGS, so
இனிமே சொல்லணும் ப்ரெஷர் செத்துறணுமாடா
see here VGS, how will we write? VG minus VS. VS is 2 volts minus VTH is 0.5. This is mod. And actually, since it is a PMOS, so let me write it as a PMOS only. SG. So it's actually 2 minus VG minus 0.5 of whole square. Now how can I write VG? If you clearly see here, VG is actually ID into 10 kilo ohms. Can you see that? Can you see this? Here this is VG, right? And I can write VG as VG equal to ID into 10 kilo ohms
Yes, ma'am.
from figure. Yeah. So the equations become ID is 1 by 2 into 2 minus ID into 10k minus 0.5 whole square. So it is a quadratic equation on ID. See, here also you have ID, here also you have ID. So we have to simply solve this quadratic equation and we'll finally get the value for ID. So can you solve this equation on your own? Our last 1 minute we have. Do you want to try this?
We'll do it, ma'am.
You'll do it?
Yes,
So
ma'am.
maybe I'll give you the final answer. So ID is 104 microamperes. What we have to do is we have to simply solve this quadratic equation, okay? And we'll get the value for ID. Is this clear?
Yes, ma'am.
Any doubts till now?
Ma'am, it's not a doubt, ma'am.
Yeah.
Ma'am, have you is the sheet of these questions available somewhere?
Is the sheet of questions available somewhere?
Sheet solving, yeah.
This particular sheet you want? So because all the questions I've already I have finished, so you won't need it. And these are actually the questions from
Actually,
previous year, so you don't have access to them. You won't be able to get
actually,
that.
only questions has also sufficed because we were just going so fast, so I couldn't note down all the questions. So I just have a solution.
Oh, okay, okay. No, no, it's okay. I'll simply upload it right now. And yeah, before drifting apart, I would like to say, so last time you must have seen my channel, right? I upload all my videos over there. So what you can do is you can subscribe to the channel. So whenever I the moment I upload it, no, you'll get it as a recommendation. So you need not to wait for the link to be shared, because I have seen that it took a long time for the team to share the link, right, with you people for last year's video.
Ma'am, where are your videos available?
They are available on YouTube.
Your channel, ma'am?
Okay, so for my channel you can write B Sharda Devi. Maybe you can. Do you want me to type it down?
Yeah, ma'am, it will help.
Yeah, so I'll type it down. So you'll find the so this is my channel. So here we are uploading, and even I have taught this subject last semester also. The questions will be different, and they were mostly based upon MOSFET. So if you want to practice and look into more problems on MOSFET, you can go through those lectures as well. so they are available. So the moment you like look into this channel, you can find all my videos, and if you subscribe, so the moment I upload it, you'll get the notification. So whatever we have solved right now, you'll get it also. So you don't have to wait for till when the NPTEL team shares the link. You'll get it immediately, because the moment I start uploading, it will be uploaded by tonight. So from tomorrow morning, you can view it and revisit the questions again. And I also share my solved sheet also. So last time, were you able to access this notes? Were you able to access the notes that I'm preparing right now?
Ma'am, since I had already seen the video, I didn't go through the video again, so I just needed
Okay.
the questions. So
Yeah,
that's
so that you can get through the notes. So
yeah.
from notes you can
Ma'am,
find.
separately notes were not available.
No, actually, we were asked to upload this notes also, and there is this one folder where I'm uploading the notes as well. So you can get this PDF which I'm preparing right now, and you'll also get the video on YouTube. So I just
We've got the mail, ma'am.
regarding both like video as well as the notes, right?
Yes, ma'am.
Yeah, yeah.
Ma'am, for notes, I don't think we have any mail for that. I'll check
Yes,
again.
ma'am. For notes, we haven't received any email.
Maybe you can check through them. And I also said that because I realized that the video which we are, so I upload them immediately, but the link is being shared with you after 4 to 5 days. So I don't want you to face that delay. So if you subscribe it, you'll immediately get the video available to you by tomorrow. Or the moment it is uploaded, you'll see in your recommendations, like YouTube recommendations, you'll get this video, whatever I'm recording right now. So you can immediately go through it. So that also you can do. This is the channel name, and just in case if you find any difficulty, we can look into it next week also. Okay.
Yes, ma'am. Thank you, ma'am.
Okay, thank you guys. So if you have any
Thank you,
concerns,
ma'am.
any queries other than this.
No, ma'am.
Okay.
Thank you. Thank you, ma'am.
Okay, see you next week. Have a good
Thank you,
day.
ma'am.
Yeah, bye everyone. Thank you.
Bye, ma'am. Thanks, ma'am.